Welcome to Btechnical. This is revision lecture 5 in continuation of geotechnical engineering revision in context of Bpsc AE advertisement number 29 by 2025. Okay, so in fifth lecture we have considered this last part of geotechnical engineering, that is foundation engineering. So in foundation engineering, first you should know the types of foundation. Okay, so there are basically two types of foundation. One is called as shallow foundation, and another is called a deep foundation. If you define basically the shallow foundation is when the depth of footing is less than the width of footing, less than equal to the width of the footing, then it is called as shallow foundation, and if it is greater than, then it is deep foundation. Okay. So shallow foundation basically classified in two types. One is called as footing, in which there are so many types of footings are there, that is spread footing, then strap footing, combined footing, and other classification of this shallow foundation is called raft footing. Okay, so in spread footing two types are there. One is isolated and other is strip footing. Okay, strip footing is just like the wall, below the wall, the footing below the wall that is along the length. This is called as strip footing, and isolated footing is a for concentrated load just below the column. It is called isolated footing. Isolated footing may be a square, circular, rectangle, like that. And raft footing is also called as mat foundation. So when so many columns are there, suppose these are the area, and 2 3 4 columns are coming on these. This column may be rectangular, circular. So for all these columns there is a common footing called as raft footing. Okay, there is also one footing comes in combined footing, that is rectangular combined footing, trapezoidal combined footing, when two columns or three columns, means two columns are combined by a single footing. Okay, then it is called as combined footing. Now these footings this shallow foundation is basically used below the when load is not so much high. So we can say below 5-story building. If you take the if you consider the case of building, then below G+4, G+5 footing is under shallow foundation. And if the soil is very loose soil, means like clay soil, means bearing capacity of the soil is very weak, at that time instead of shallow foundation we can use raft foundation. Okay, under shallow foundation we can use this raft footing when bearing capacity of the soil is very less. Another type is deep foundation. In deep foundation there is pile foundation, then pier foundation, and well foundation. These types of foundation are basically used in high rise building when story of the building is more than 30 meter, 40 meter, 60 meter. 40-story building, 30-story, 60-story building, 80-story building. Below that we can use this deep foundation, high rise building. Other is breeze. In case of breeze, foundation of breeze. There are so many types of pile, that is end bearing pile, friction pile, which we'll discuss in later part of this lecture. Now come to the bearing capacity calculation. One is called as gross bearing capacity. Gross bearing capacity, what are the total load coming on the footing, that divided by area of the footing is called gross bearing pressure. The total gross load divided by total area is called gross bearing pressure. And after that, net bearing pressure, when you subtract the overburden pressure, that is gamma dF, from the gross pressure, then it is called as net bearing pressure, Qn. Okay, so Qn is nothing but Qg minus gamma dF, where gamma dF is the overburden pressure. Whatever be the depth of footing, you know the footing is always below the ground level. Suppose here is the footing, here is the footing. So these are called as depth of the footing. So ground level is basically here. Okay, so this depth is called as depth of the footing. So that much overburden pressure, this soil pressure is coming on the here, this pressure is also coming. So when you subtract this overburden pressure which is above the footing, then it is called as net bearing pressure. After that, net ultimate safe bearing capacity is QNS, that is when you consider some factor of safety in net bearing pressure. So net bearing pressure, net ultimate bearing pressure divided by factor of safety, then it is called as a safe net bearing capacity. Okay, and last one is called safe bearing capacity. So when in QS, when ultimate bearing capacity minus gamma df, this overburden pressure, so this pressure is called as net bearing pressure divided by factor of safety, then it is called as net ultimate safe bearing capacity. And when you add again overburden pressure in this net ultimate safe bearing capacity, then it is called as safe bearing capacity, QNS, QS, safe bearing capacity. Now the depth of footing, minimum depth of footing is not less than 0.8 to 0.9 meter, and there is some formula which give you the depth of footing calculation, that is given by the Rankine theory. And Rankine theory is told that minimum depth of footing is Q upon gamma into 1 minus sin phi divided by 1 plus sin phi whole square. From this formula you can calculate the minimum depth of the footing, and it should not be less than 0.8 to 0.9, where Q is the intensity of the loading. Again there is some theory which calculate which give you the exact formula to calculate the ultimate bearing capacity. So the scientist given is Carl Terzaghi. You know, this Carl Terzaghi is also called as father of geotechnical engineering. Geotechnical engineering. Father of geotechnical engineering is called Carl Terzaghi. So according to Terzaghi's equation for strip footing, you have to remember this formula is for strip footing for generalized soil. Okay, that is QU is equal to CNC plus gamma DF NQ plus 0.5 gamma B N gamma. This part is for sandy and this part is for clay soil. Means if clay is there, then CNC and C comes for clay, and if there is a some friction in the soil, that is for sand. Okay, so the total formula is like this, in which NC, NQ and N gamma, NC, NQ, N gamma is the factors which depends on phi. Phi is the friction angle of the soil. Okay, so these factors are depends on phi. There is also some expression to calculate the NC, NQ, N gamma, but as of now we not required this NC, N gamma and NQ calculation, as it is already given in objective question, but you can calculate. So I am not consider this expression. But you should know there is a expression to calculate this NC, NQ and N gamma, which depends on the phi. Next is here, if the soil is cohesive soil, then you know for cohesive soil friction in phi is equal to 0, and if phi is 0, then this term will is 0, and if this term is 0, then the pressure is QU is equal to 5.7 C plus gamma DF. Here 5.7 is the NC value. 5.7 is the value of NC, which is given by Terzaghi. So according to Terzaghi, if the soil is cohesive, then QU is equal to 5.7 C plus gamma DF, and if you calculate the net safe bearing capacity, then Q means net pressure QNU, then it is equal to QU minus gamma DF. So gamma DF will cancel. So this is equal to QU, and QU is 5.7 NC, sorry 5.7 C, because NC value is 5.7. So for net pressure this is 5.7 NC. So numerical question for objective is directly asked on this question. If C is given, you can calculate the net pressure in cohesive soil. According to Terzaghi, this value is 5.7. Next is effect of water table. What are the effect of water table on bearing capacity? Obviously, if water table is there, which is either some distance below the footing or above the footing, then it definitely affect the soil bearing capacity of the soil, means it reduce the bearing capacity. Okay, so the formula for this is Q is equal to CNC gamma DFNQ. Here is the water correction factor RW1, and 1 by 2 gamma B and gamma. Here is the water correction factor RW2. So these two terms affect the bearing capacity of the soil if water table is there. So RW1 is in second term is the reduction factor when water table is above base level. Reduction factor when water table is above base level, and reduction factor when water table is below base level. Okay, so RW1 and RW2 should not be greater than 50%. Should not be greater than 50%. Its value should not cross the 50%. There is some formula also for to calculate this RW and RW2. I didn't have considered again. I not consider for this lecture because if you consider all these things and describe all the things, the lecture becomes too lengthy, and it's doesn't meaning a revision lecture for that. Okay, so this is the footing. If this is the footing, this depth width is B. So when water table is in this zone, when water table is in this zone, so there are so many condition, three condition. When water table is below the footing and below the depth which is equal to base of the footing. Okay, and second condition is when at the base of the footing. Third condition is when between ground level and just above the footing, and when at the ground level of the water table is at the ground level. At that case the value is equal to 0.5. Okay, so there are so many conditions that you need to study from the book. Okay, next part is there is a modified equation for other shape as you discuss here. This equation is for strip footing. Okay, so there is so many types of footing. If the shape of the footing is square, if the shape of the footing is square, then here one factor has come, that is 1.3, and here one factor has come, that is 0.4. Okay, instead of 0.5 it is 0.4. So 1.3 CNC gamma DF NQ, 0.4 gamma B and gamma for square footing. And if it is circular footing, this factor remains same, only this factor have changed. That is 0.3 gamma B and gamma. And if it is rectangular footing, then you need to calculate this factor, that is 1 plus 0.3 B by L, where B is the width of the footing, L is the length of the footing. This term is again same, and in this term you need to calculate this value, that is 1 minus 0.2 B by L. Here is the 1 plus 0.3 B by L, here is the 1 minus 0.2 B by L. So these two factor you need to calculate, and you have to remember this formula for rectangular footing. Okay, so this is based on again the Terzaghi's equation. And if you consider another theory that is given by the Scamptons given another theory from which he has calculated the different value of this NC value in the same formula, only NC value have changed. As you know, for NC value according to Terzaghi is 5.7. For so for Scamptons, if depth by width of the footing is less than 0, then for strip footing its value is 5, and for square footing its value is 6, for rectangular footing its value is 6. So minimum value of NC for strip, square and rectangular footing is 5, 6 and 6. Okay, now if this value is greater than 2.5 meter, means if the ratio of depth of footing to the width of footing is greater than 2.5 meter, then the maximum value for the NC is 7.5 in strip footing, 9 in square footing, and again 9 in rectangular footing. And if this value, means depth of footing and to the width of footing ratio is lies between 0 to 2.5. In that case, you need to calculate this value. For stiff footing, that is 5 multiplied by 1 plus 0.2 df by b, whatever be the ratio, that multiplied by 0.2 plus 1 and whole multiplied by 0.5. This value you need to remember for the case when depth to width ratio is lies between 0 to 2.5. So this is for stiff footing, this is for square footing, and this is for rectangular footing. Another is Meyerhof equation. Meyerhof consider there is different factors, that is correction factor for each term, each term, that is NC, NQ and N gamma. For each term there is 3 correction. One is SC, shape correction factor, another is DC, depth correction factor, another is IC, inclination correction factor. These 3 factor he introduced, and the formula is remain the same. Only you need to know these 3 factors: depth, shape and inclination correction factor. Our IS code also adopt the theory of Meyerhof equation to calculate the bearing capacity, ultimate bearing capacity of the soil. Next one is ultimate bearing capacity as per shear criteria. As you know, foundation is designed by either shear criteria or by settlement criteria. Okay, so based on shear criteria, for clay soil, QUF is QUP. So failure strength is equal to the ultimate strength. But in case of sand, the failure strength, that is QUF to QUP ratio, is equal to BF upon BP. So here B suffix F and B suffix P is the width of footing. This is for footing, and this is for plate. This is for plate, whatever be the size of the test plate. So if these 3 values given, you can automatically calculate the 4th one. So small objective numerical question may ask on this formula. And next one is safe settlement criteria, based on settlement criteria. Okay, this is for shear criteria and this is for settlement criteria. So based on settlement criteria, if the soil is clay, then settlement is come in the consideration, SF upon SP. Again here the P suffix is used for plate, F suffix is used for foundation. Okay, so SF upon SP is equal to B suffix F upon BP, and for sand this value is SF upon SP is equal to BF bracket BP plus 0.3 divided by BP into BF plus 0.3, this whole raised to 2, raised to the power 2, that is square of this whole term. Okay, so from here you can consider the settlement in the foundation. Okay, this formula asked many times in previous exam, directly formula and numerical also based on this 3 formula. So IS code given the settlement for clay, clay is 40 mm and for sand is 25 mm in case of differential settlement. Okay, so for differential settlement, IS code recommended this settlement value. Okay, and if it is for isolated footing, then clay value is settlement for in clay soil is 65 and in sand it is 40, and for raft footing, this is for isolated, this is for raft footing. Raft footing, if the soil is clay, then this value, the settlement value may rise from 65 to 100, and for sand it is 40 to 65. Okay, so we stop here for this lecture. Will again come another lecture to bind up this foundation engineering. Okay, bye bye, take care.